Hello, in this lecture we'll find out the area of the green triangle. In the drawing we have a quarter circle. Inside the quarter circle we have line segment PQ that is equal to 4 units, line segment AQ equals to 5 units, and this angle APQ equals to 90 degrees. Our mission is to find out the area of the green right triangle AQO. Okay, so first of all we focus on the right triangle APQ, on the right yellow triangle APQ. And we will implement the Pythagoras theorem on this right yellow triangle APQ. Here by PT is the abbreviation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So the hypotenuse in the yellow right triangle APQ is AQ. Therefore, the square of the hypotenuse is AQ squared. And it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to PQ squared plus AP squared. Repeat again. In the right yellow triangle APQ, according to the Pythagoras theorem, AQ squared equals to PQ squared plus AP squared. So AQ equals to 5, therefore Q squared is 5 squared, that is 25. And it is equal to PQ squared. PQ is 3, therefore PQ squared is 3 squared, that is 9, plus AP squared. In conclusion, found out that according to the Pythagoras theorem, the yellow right triangle 25 equals to 9 plus AP squared. We subtract 9 from this equation and we get that 25 minus 9 is 16 equals to AP squared. We take a root out of this equation and we get that AP equals to the square root of 16, that is 4. AP equals to 4 units. I write it down in the drawing that AP equals to 4 units. Here we have a quarter circle. You can easily complete this quarter circle to a circle, and then the center of the circle will be at this point, point O. And we have also rule number 2 that says that if you draw a peripheral angle from the center of the circle towards any chord, it will bisect the chord. I repeat on rule number 2. According to rule number 2, a peripheral angle from the center of a circle towards any chord bisects the chord. The center of this circle is here at point O. If you draw a perpendicular from point O towards chord BC, here this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point O and BC as M. According to rule number 2, the perpendicular OM bisects chord BC. Again, the perpendicular OM bisects chord BC. That is to say, it divides it into two halves. The first half is Bm and the second half is Mc. Therefore, Bm equals to Mc. We can implement this rule number 2 in our drawing. From the center of the circle, that is to say from point O, we will draw perpendicular on chord AP. Again, from point O, the center of the circle, we will draw perpendicular on chord AP. So, this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AP is M. According to rule number 2, the perpendicular OM bisects chord PA. But PA equals to 4, so the perpendicular OM divides it into two halves. The first half is PM, that is equal to 2, and the second half is MA, that is also equals to 2, of course. In the next step, we define the intersection point between perpendicular OM and line segment AQ as N. We define angle PAQ as theta. If you focus on the right yellow small triangle AMN, this angle equals to theta. This angle equals to 90 degrees, therefore the missing angle, this angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees, exactly according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Likewise, if you focus on the big yellow triangle, big yellow right triangle APQ, this angle equals to theta, this angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus theta. Okay. In the next step, we'll prove that the small yellow right triangle AMN is similar to the big yellow triangle APQ. Again, the big triangle the big right yellow triangle APQ is similar to the small yellow right triangle AMN. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So I write it down. Angle APQ in the big triangle equals to angle AMN in the small triangle. They are both equal to 90 degrees, therefore they are equal to each other. I repeat again. Angle APQ in the big triangle equals to angle AMN in the small triangle. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this angle theta, is a common angle that belongs to both triangles. So angle theta equals to itself. We call to angle theta two different names. Angle theta equals to PAQ, angle PAQ, and it is equal to itself. Angle theta also called MAN. Repeat again. Angle theta equals to itself as a common angle. It means that angle PAQ in the big triangle is actual angle theta equals to angle MAN in the small triangle that is also angle theta. So those are two different names for the same angle theta. It is equal to theta. It is a common angle that belongs to both triangles. So angle theta equals to itself. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So angle AQP in the big triangle equals to angle ANM in the small triangle. They are both equal to 90 degrees minus theta, therefore they are equal to each other. Repeat again. Angle AQP in the big triangle is equal to angle ANM in the small triangle. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So we actually proved that all three angles in the big triangles are correspondingly equal to all the three angles in the small triangle. Therefore, those two right yellow triangles are similar to each other according to angle similarity rule. So I write it down. The big triangle, the big yellow triangle APQ is similar. This is the sign of similar to the small yellow triangle, the small yellow right triangle AMN. According to angle similarity rule. So what is angle similarity rule? Angle similarity rule is that if all three angles in one triangle are correspondingly equal to all three angles in another triangle, then the two triangles are similar to each other according to angle similarity rule. From the fact that the two triangles are similar to each other, we conclude that PA in the big triangle over MA in the small triangle equals to PQ in the big triangle over MN in the small triangle, and it is equal to QA in the big triangle over NA in the small triangle. I repeat again. PA over MA equals to PQ over MN equals to QA over AN. So PA equals to 4 units. Here PA equals to 4 units. MA equals to 2 units. And it is equal to PQ that is equal to 3 units. Over MN is unknown. Over QA equals to 5 units. QA equals to 5 units according to what is given as the equation. Over NA that is unknown. So in conclusion, I found out that 4 over 2 equals to 3 over NM equals to 5 over NA. From this equation, we will conclude that 4 over 2 equals to 3 over MN. 4 over 2 equals to 3 over MN. Four over 2 is 2. 2 equals to 3 over Mn. We multiply this equation by Mn. And we get that 2 times Mn equals to 3. We divide this equation by 2, and finally we will get that Mn equals to 3 over 2, that is 1.5. Mn equals to 1.5 units in its length. I write it down in the original drawing that Mn equals to 1.5 units in its length. So, from this equation, we will conclude that 4 over 2 equals to 5 over An. Again, 4 over 2 equals to 5 over Na. 4 over 2 equals to 5 over Na. Four over 2 is 2, and 2 equals to 5 over Na. We'll multiply this equation by Na, and we'll get that 2 times Na equals to 5. We'll divide this equation by 2, and finally we'll get that Na equals to 5 over 2, and 5 over 2 is 2.5. Na equals to 2.5 units in its length. I will write it down. That 97 Na equals to 2.5 units in its length. Here. What is the length of line segment Qn, or NQ? The length of line segment Qn, it is very easy to see from the drawing that Qn equals to AQ minus AN. Okay, Qn equals to AQ minus AN. I write it down. Qn equals to AQ minus AN. Repeat again. Qn equals to AQ minus AN. So Qn equals to AQ is 5 minus AN is 2.5. So in total, Qn equals to 5 minus 2.5. Qn equals to 5 minus 2.5 is 2.5 units. Qn equals to 2.5 units in its length. I write it down. Qn, this time segment Qn, equals to 2.5 units in its length. We know that any triangle can be blocked by a circle. Again, any triangle can be blocked by a circle. Therefore, we will block the right green triangle AQO by a circle. So I will copy this green triangle in a new page, and we will block it by a circle. So this is the right green triangle that I copied from the original drawing. Now we will block it by a circle. Okay, so inside this circle we have peripheral angle AOQ that is equal to 90 degrees. Again, peripheral angle AOQ equals to 90 degrees in its size. And we have rule number 5 that says that any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. I'll repeat again. any peripheral angle that is equal to 90 degrees rests on the diameter of the circle. Here peripheral angle ABC equals to 90 degrees, therefore it rests on the diameter of the circle. AC is the diameter of the circle. Okay? So here, peripheral angle AOQ that is equal to 90 degrees must rest on the diameter of the circle. Therefore, AQ is the diameter of the circle. Again, because of the fact that peripheral angle AOQ equals to 90 degrees, therefore it must rest on the diameter of the circle. Therefore, AQ is the diameter of the circle. AQ is the diameter of the circle. The diameter of any circle equals to 2 times the radius. So it is 2r, and it is given as the equation that AQ equals to 5 units. From this equation, we will derive that 5 equals to 2r. 5 equals to 2r. We will divide this equation by 2, and we will get that r equals to 5 over 2 is 2.5. The radius of this circle equals to 2.5 units. In the next step, I will copy point N from the original drawing to our drawing. This point N. So this is point N that I copied from the original drawing. We have already found out that AN equals to 2.5. And also NQ equals to 2.5 here. But we just right now found out that the radius of the circle also equals to 2.5. Therefore, QN, that is located on the diameter of the circle, that is equal to 2.5, must be the radius of the circle. So, QN is the radius of the circle, that is equal to 2.5. Likewise, NA that is located on the diameter of the circle and it is equal to 2.5 must be the radius of the circle. The radius of the circle is NA that is equal to 2.5. Okay, so we have on the diameter of the circle 2 radii, and therefore the intersection point of those 2 radii must be the center of the circle. The intersection point occurs at point N, therefore point N is the center of the circle. N is the center of the circle. N is the center of the circle. We join points N and O together by a straight line. What is the definition of line segment NO? Line segment NO starts from point N that is the center of the circle and ends at point O that is the point of the circle itself. This is exactly the definition of a radius. So NO is the radius of the circle that is equal to 2.5 units. So NO equals to, is the radius of the circle that is equal to 2.5 units in its length. In the next step, we will implement the Pythagoras theorem on the right triangle OMA. So I will copy the right triangle OMA in a new page and we will implement on it the Pythagoras theorem. Side MA equals to 2 units. What is the length of side MO? From the drawing it is very easy to see that MO equals to MN plus NO. MO equals to MN plus NO. MN equals to 1.5. NO equals to 2.5. Therefore, in total, MO equals to 1.5 plus 2.5, that is 4. So MO equals to 4 units. This is the right triangle OMA that I copied from the original drawing. Now we will implement on this right triangle OMA the Pythagoras theorem. According to the Pythagoras theorem, this right triangle OMA, the square of the hypotenuse, that is to say OA square, must be equal to the sum of the sides of the perpendiculars, that is to say it must be equal to OM square plus MA square. Okay? OA square equals to OM square plus MA square. So OA square equals to OM square. OM is 4, therefore OM square is 4 squared, that is 16, plus MA square. MA is 2, therefore MA square is 2 squared, that is 4. So in conclusion, we found out that OA square equals to 16 plus 4, that is 20. We'll take a root out of this equation, and finally we will get that OA equals to the square root of 20. Okay, OA equals to the square root of 20. So we write in the original drawing that OA equals to the square root of 20 units in its length. And finally, we'll implement the Pythagoras theorem on the right triangle AQO. So I'll copy the right triangle AQO in a new page and we'll implement on it the Pythagoras theorem. AOQ AQ equals to 5 units, the hypotenuse AQ equals to 5 units, and AO equals to the square root of 20 units. So actually, this is the right triangle AQO, the right triangle that I copied from the original drawing, AQO. Now we will implement on this right triangle the Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse is AQ square. It is equal to the sum of the sides of the perpendiculars. That is to say, it must be equal to AO square plus QO square. So AQ equals to 5, therefore AQ square equals to 5 square, that is 25. And it is equal to AO square. AO equals to the square root of 20, therefore AO square equals to the square root of 20 square, that is 20, plus QO square. We subtract 20 from this equation, and we get that 25 times 20 is 5, equals to QO square. We take a root out of this equation, and finally we get that QO equals to the square root of 5 units. QO equals to the square root of 5 units. QO equals to the square root of 5 units. Now it is very easy to find out the area of the green triangle, the green right triangle AOQ. So the area of the green right triangle AQO here, the square brackets is the sign for the area. It means the area of triangle AQO equals to the area of any triangle equals to the base of the triangle times the height to the base. The height must create 90 degrees with the base over 2. That is the area of any triangle. The base of the green right triangle will be QO, and the height is AO. Why the height is AO? Because AO creates 90 degrees with the base QO. So it is, the height is AO over 2. Repeat again. The base is QO, the height is AO over 2. QO equals to the square root of 5. AO equals to the square root of 20 over 2. In conclusion, we found out that the area of triangle AQO equals to the square root of 5 times square root of 20 over 2. We have the algebraic identity that the square root of A times square root of B equals to the square root of A times B. According to this algebraic identity, you get that the square root of 5 times square root of 20 equals to the square root of 5 times 20 over 2. 5 times 20 is 100, so the square root of 100 the square root of 100 over 2 is the area of the green rectangle AQO. The square root of 100 is 10, and 10 over 2 is 5. So finally we found out that the area of the green right triangle AQO equals to 5 square units. Repeat again. The area of this green right triangle AOQ equals to 5 square units. In the next step, I will summarize the lecture. So, in the drawing, we have a quarter circle. Inside the quarter circle, we have line segment AQ that is equal to 5 units, line segment PQ equals to 4 units, angle APQ equals to 90 degrees, and our mission is to find out the area of the green right triangle AQO. So, we implemented the Pythagoras theorem on the right yellow triangle APQ. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the yellow triangle APQ is AQ, therefore the square of the hypotenuse is AQ squared, and it must be equal to the sum of the squares of the perpendiculars, that is to say it must be equal to PQ squared plus AP squared. Repeat again, according to the Pythagoras theorem, in the right yellow triangle APQ, AQ squared equals to PQ squared plus AP squared. AQ equals to 5, therefore AQ squared is 5 squared, that is 25. PQ equals to 3, therefore PQ squared is 3 squared, that is 9, plus AP squared. Subtracted 9 from this equation and found out that 25 minus 9 is 16, so 16 equals to AP squared. We took a root out of this equation and found out that AP equals to the square root of 16, that is 4. So here, line segment side PA equals to 4 units. Okay, here we have a quarter circle. AOB is a quarter circle. Actually, you can complete this quarter circle to a circle, and then point O will be the center of the circle. So point O is the center of the circle, and we have rule number 2 that states that whenever you draw a perpendicular from the center of the circle towards any chord, it will bisect the chord. Repeat again on rule number 2. any perpendicular perpendicular from the center of a circle towards any chord, bisect the chord. The center of the circle is here at point O. From point O, we draw perpendicular on chord BC. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and BC as M. So the perpendicular OM bisects chord BC. It means that it divides chord BC into two halves. The first half is BM and the second half is MC. And the fourth BM equals to MC. So whenever we draw a perpendicular from the center of the circle towards any chord, it will bisect the chord. In this case, the perpendicular OM bisects chord BC, that is to say BM equals to MC. So we can implement rule number 2 in our drawing. From the center of the circle, that is to say from point O, we draw perpendicular on chord PA. This angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We defined the touching point of the perpendicular from point O and PA as M. And according to rule number 2, the perpendicular OM from the center of the circle, that is to say from point O, bisect chord PA. And PA equals to 4, and the perpendicular OM divides this into two halves. It means that the first half is PM, that is equal to 2, and the second half is MA, that is also equals to 2. In the next step, we define the intersection point between perpendicular OM and line segment AQ as N. Then we define the angle PAQ as theta. So in the right small yellow triangle AMN, this angle equals to theta. This angle equals to 90 degrees. Therefore, the missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. That is the sum of the angles in any triangle. Likewise, in the big yellow triangle APQ, this angle equals to theta. This angle equals to 90 degrees. Therefore, the missing angle must be equal to 90 degrees minus theta. Then we proved that the small yellow triangle AMN, the small yellow white triangle AMN, is similar to the big yellow white triangle APQ. So why those two white triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. I'll repeat again. Angle APQ in the big triangle is equal to angle AMN in the small triangle. They are both equal to 90 degrees, therefore they are equal to each other. In addition, angle theta is a common angle that belongs to both triangles, therefore angle theta equals to itself. We actually called angle theta two different names. Angle theta equals to, angle theta is actually angle PAQ that belongs to the big triangle, and angle theta is also angle AMN that belongs to the small triangle. Okay, so here we have angle PAQ in the big triangle, that is actually angle theta, equals to angle MAN in the small triangle, that is also angle theta. There are two different names for the same angle, and it is equal to theta. It is a common angle that belongs to both triangles, so angle theta equals to itself. And finally, those two angles that are both equal to 90 degrees minus theta, therefore they are equal to each other. So angle APQ in the AQP in the big triangle is equal to angle ANM in the small triangle. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So we actually succeeded to prove that all three angles in the big triangle are correspondingly equal to all three angles in the small triangle. Therefore, we proved that those two triangles are similar to each other according to angle similarity rule. Here, the big triangle, the APQ, is similar to the small triangle AMN according to angle similarity rule. What is angle similarity rule? Angle similarity rule is that if you prove that all three angles in one triangle are correspondingly equal to all three angles in another triangle, then you actually proved that those two triangles are similar to each other according to angle similarity rule. Okay. For the fact that the two triangles are similar to each other, we will conclude that PA in the big triangle over MA in the small triangle equals to PQ in the big triangle over MN in the small triangle, and it is also equals to QA in the big triangle over NA in the small triangle. I'll repeat again. PA over MA equals to PQ over MN equals to QA over AN. PA equals to 4 units over MA equals to 2 units. PQ equals to 3 units, and MN is unknown, and QA equals to 5 units, and NA is unknown. In conclusion, found out that 4 over 2 equals to 3 over MN equals to 5 over N equals to 5 over NA. From this equation, we will conclude that 4 over 2 equals to 3 over MN, 4 over 2 equals to 3 over MN, 4 over 2 is 2, so 2 equals to 3 over MN. We multiplied this equation by Mn, and we found out that 2 times Mn equals to 3. We divided this equation by 2 and found out that Mn equals to 3 over 2, that is 1.5. Again, Mn equals to 1.5 units in its length. This line segment Mn equals to 1.5 units. Then, from this equation, we will conclude that 4 over 2 equals to 5 over An. 4 over 2 equals to 5 over An. 4 over 2 is 2, so 2 equals to 5 over An. We multiplied this equation by An and found out that 2 times An equals to 5. We divided this equation by 2 and finally found out that An equals to 5 over 2, that is 2.5. Okay, An or Na equals to 2.5 units in its length. This line segment Na equals to 2.5 units in its length. What is the length of line segment NQ? From the drawing, it is very easy to see that NQ equals to AQ minus AN. Again, NQ equals to AQ minus AN. I'll repeat again. NQ equals to AQ minus AN. AQ equals to 5. AN equals to 2.5. AN equals to 2.5. So in conclusion, we found out that QN equals to 5 minus 2.5. That is 2.5. So QN, line segment QN equals to 2.5 units in its length. This line segment QN equals to 2.5 units in its length. We know that any triangle can be blocked by a circle. Again, any triangle can be blocked by a circle, and therefore we'll block the right triangle AOQ by a circle. So I copied the right triangle in this page. This is triangle AOQ that I copied from the original drawing. And we blocked this triangle by a circle. Okay? So inside this circle, we have peripheral angle AOQ that is equal to 90 degrees. This peripheral angle AOQ equals to 90 degrees. And we have rule number 5 that any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. Repeat again. According to rule number 5, any peripheral angle that is equal to 90 degrees rests on the diameter of the circle. Here peripheral angle ABC equals to 90 degrees, and therefore it rests on the diameter of the circle. AC is the diameter of the circle. Okay. We can implement rule number 5 in our drawing. Because of the fact that peripheral angle AOQ equals to 90 degrees, therefore it must rest on the diameter of the circle. That is to say, AQ is the diameter of the circle. Very simple. Okay. So AQ is the diameter of the circle. We know that the diameter of any circle equals to 2 times the radius, so it is 2r. And it is given as the equation also that AQ equals to 5 units. From this equation, we conclude that 2r equals to 5, or 5 equals to 2r. We divided this equation by 2, and finally we found out that r equals to 5 over 2, that is 2.5 units. The radius of this circle equals to 2.5 units. In the next step, I copied point N from the original drawing to our drawing here. Okay, this is point N that I copied from the original drawing. We already found out that AN, line segment AN equals to 2.5, and line segment NQ equals to 2.5 also. Line segment NQ equals to 2.5. AQ is the diameter of the circle. And the radius of this circle is 2.5. If AQ is the diameter and the radius of the circle equals to 2.5, NQ that is also equals to 2.5 and it is located on the diameter must be the radius of the circle. NA that is also equals to 2.5 must be the radius of the circle. Okay? And the touching point of those two radii, AN and QN, must be the center of the circle. Okay? Very simple. The touching point between the two radii along the diameter of the circle must be the center of the circle. Here, point N is the center of this circle. We join points N and O together by a straight line. What is the definition of line segment NO? Line segment NO starts from point N, that is the center of the circle, and ends at point O, that is the point of the circle itself. This is exactly the definition of a radius. Therefore, NO is the radius of the circle, that is equal to 2.5 units. Here, NO is the radius of the circle, that is equal to 2.5 units. In the next step, we copied the right triangle AMO in a new page, and we implemented on this right triangle AMO the Pythagoras theorem. Side AM equals to 2 units, and side MO equals to MN plus NO. So MO equals to MN, that is 1.5, plus NO, that is 2.5. 1.5 plus 2.5 is 4, so in total MO equals to 4 units. So actually, this is the right triangle OMA that I copied from the original drawing. Implemented on this right triangle OMA the Pythagoras theorem. According to the Pythagoras theorem, in this right triangle, the square of the hypotenuse is AO square, and it must be equal to OM square plus MA square. OA square equals to OM square plus MA square. So OA square equals to OM square. OM equals to 4, therefore OM square is 4 square, that is 16. Plus MA square. MA equals to 2, therefore MA square equals to 2 square, that is 4. So OA square equals to 16 plus 4, that is 20. OA square equals to 20. We took out of this equation and found out finally that OA equals to the square root of 20 units. So I wrote down here in the drawing that OA equals to the square root of 20 units. In the next step, I copied the right green triangle AQO in a new page, and we implemented on this right green triangle the Pythagoras theorem. This is the right triangle AQO that I copied from the original drawing. AO equals to square root of 20 and AQ equals to 5. Here. According to the Pythagoras theorem, the square of the hypotenuse is AQ square, and it must be equal to AQ square, and it must be equal to AO square plus QO square. Again, AQ square equals to AO square plus QO square. AQ is 5, therefore Q square is 5 square, that is 25. plus AO squared. AO is square root of 20, therefore AO squared is square root of 20 squared, that is 20, plus QO squared. We subtracted 20 from this equation and found out that 25 minus 20 is 5. 5 equals to QO squared. We took a root out of this equation and found out that QO equals to the square root of 5 units. So here QO equals to the square root of 5 units. Now it is very easy to find out the area of the green triangle AQO. Okay, that is the triangle that we are looking for. The area of this triangle AQO. Here the squared bracket is the sign for the area. It means that the area of triangle AQO equals to the area of any triangle is the base of the triangle times the height over 2. The height must create 90 degrees with the base. The base is QO and the height is AO. Why the height is AO? Because the height AO creates 90 degrees with the base QO. Again, the base is QO, the height is AO over 2. QO equals to the square root of 5 units. AO equals to the square root of 20 units. Okay? So QO is square root of 5 units, AO is square root of 20 units over 2. We have the algebraic identity that the square root of A times square root of B equals to the square root of A times B. Therefore, according to this algebraic identity, we will get that the square root of 5 times square root of 20 equals to the square root of 5 times 20 over 2. 5 times 20 is 100. So inside the root we have 100 over 2. The square root of 100 is 10, and 10 over 2 is 5. So in conclusion, we found out that the area of this right green triangle AQO equals to 5 square units. The area of the green right triangle AQO equals to 5 square units. Okay, thank you very much.